Okay, it's working.
Okay. All right, I think we're ready to go here. I can't get to speaker view, but there we go. I think we're ready to go. Folks, I'm sorry, we had the electricity went out here, and fortunately, my wife, technologically wizard that she is, that would go through her phone, and so we hope everything's fine, and Becca has power, so we're ready to go. Thanks for your patience. I want to give again, as I did last time, a little background to the Earth Care Forums and the rationale for why we do this. And this has been going on for probably 6 or 7 years, but this is the first time we've been virtual. I want to say that it's initiated by the ECO team at First Presbyterian Church, which is an Earth Care congregation of the Presbyterian Church that asks that if you want to be an Earth Care, you need to promote sustainability and environmental care for the earth in your worship, education, and your plant, and also in outreach. And so we're joined also with Lawrence Ecology Teams United Sustainability, which is an important part that First Pres is part of, where it is an advocacy group for policy changes at the local to regional, including the state, of course, regarding sustainability policies that need to be advocated. And we've been to the City Commission for many things. So the lettuce itself is made up of several green teams from First Presbyterian Church, of course, and the Lawrence Jewish Community Congregation, the Unitarian Universalist Congregation of Lawrence, the Plymouth Congregational Church, Oriented Friends, the Quakers, St. John the Evangelist Catholic, Trinity Episcopal, and the Islamic Center of Lawrence. So with that, I want to say a few words about Becca. She is a PhD candidate in biosystems engineering and a graduate researcher at the Controlled Environment Agriculture Center in Tucson, Arizona. She holds a BS in environmental science and a BA in Arabic from Tufts University. Becca is a recipient of the 2021 Marshall Foundation Dissertation Fellowship and the 2020 Rachel Carson Scholars Program Fellowship, which cultivates and advances interdisciplinary environmental scholarship at the University of Arizona. She also held a 2-year fellowship with the National Science Foundation, the National Research Traineeship, Indigenous Food, Energy, Water Security, and Sovereignty Program at the University of Arizona. Her research centers on increasing the sustainability, efficiency, and accessibility of controlled environmental agricultural systems. And the question is, what is the optimal design for a greenhouse production system that not only supports local resource use efficient agriculture, but also can meet its own energy demands? And this question inspires her dissertation work, which she's now working on, looking at semi-transparent thin film solar cells for integration with greenhouse systems. Other ongoing projects include the development of holistic design approaches for controlled environmental agriculture systems to optimize plant health, as well as environmental and business sustainability. In her presentation, she'll probably clarify a lot of that. I do want to say that, of course, you're muted now, but if you would, use the chat to ask questions, which we will have time towards the end of Becca, or comments. You can do that, or you can also identify if you're from out of state, or as we had last week, or from out of town, well, let us know. And this will be recorded, and we are working on having all of the sessions on recording and available to you. Enough of that. It's time for Becca, and Becca, welcome. Thank you so much for taking the time.
Thank you, Thad. I'm gonna go ahead and share my screen now. Okay, is this visible to all? Good, good. Okay, yeah, thank you for the introduction. And as Thad described, I'll be discussing my dissertation research, which is looking at the integration of organic photovoltaics into greenhouse crop production systems. Recently, I've started to use the term tattooing your greenhouse with semi-transparent solar panels to describe this system concept. And we'll get into what all of those things mean a little bit later on. But again, my name is Rebecca Waller, and I am a PhD candidate at the University of Arizona in Biosystems Engineering. And I do my research on controlled environment agriculture systems, which is to say greenhouses or indoor farms, any system which utilizes a protective covering around a crop and attempts to control climate conditions inside of the structure in order to achieve more optimal growth conditions for the plant. I'm in Lawrence, Kansas, in case anyone was wondering. I'm Thad and Linda's next door neighbor. Came to be here. In summary, my partner had a non-remote job opportunity offer in Lawrence, and I had a remote working opportunity. So we've been living here for several months, and it's been a wonderful experience. And thank you all for, allowing us to live in such a great community. But I wanted to start out this discussion with David Attenborough. Some of you might be familiar with him and his most recent installment. It came out on Netflix several months ago. And it's basically an autobiographical account from Sir David of his life and times in 20th and early 21st century as an explorer, a naturalist, a conservationist. And it's an incredibly sad film to watch because it's looking at the systematic deterioration of the planet over the course of David's life. So it's disappointing and hard to watch, but at the end, he ends it with a more optimistic note and proposes these 4 solutions that we can take in order to save the planet. And he qualifies this statement, save the planet, by saying it's saving the planet from the human species and essentially saving the human species from ourselves, because the fact is the planet will continue on after the conclusion of the human race. But what can we do now in order to sustain the future of the human species and all of the creatures and life on the planet as well? So these 4 solutions are pretty sweeping. And the first one is obvious. It's just to slow human population growth. There won't be as many human-related problems if there aren't as many of us around, right? The second solution is the protection and restoration and conservation of our important oceanic ecosystems. But the third and fourth solutions that David proposes are what I want us to focus on. And first, the third solution is reducing our reliance on fossil fuel-based energy sources. And that means we're transitioning to renewable energy sources, such as wind energy or photovoltaic energy that you see here. Photovoltaic is, just to say, a device that converts light into electricity, and AKA solar cell or solar panel. The application of different renewable energy resources is very locationally dependent. It wouldn't make as much sense to have a massive solar panel, so photovoltaic farm in Greenland as it would in where I'm from, a place like Arizona with high solar insolation. So I also want us to start thinking about land use. Looking at this picture, a beautiful pasture covered with a smattering of renewable energy technologies. But is this really viable to just cover every open square foot of our land with renewable energy technologies? How are we going to balance land uses and land needs between residences, food production, energy generation. All of these things need to be balanced. In addition to what David focuses a lot on in this film, which is returning some of more land to its wild, natural state. And you can debate about what natural means, but just a return to a more, to rewild our environment, essentially. So the fourth solution that David proposes to save our planet is twofold. And that is first, for all of us to eat less meat, just given the huge environmental impact of meat production, of dairy production. Not to say we all, go cold tofu on meat and give it up forever, but just to reduce our meat intake would make a lot of difference. And with this, it's obvious if you're not eating as much meat, then you're eating more plants, right? So that's the second part of this fourth solution. And that's the fact that we need to upgrade to more efficient crop production systems. And what you're looking at here was also mentioned in the film. And this is on the left, an aerial view of the Netherlands. And some of you may have heard or read stories recently about the incredible progress that the Dutch have made in their horticultural industry in the past several decades through technological advances and just hard work. This tiny European country is now the second largest exporter of vegetables in the world. And that is because of their greenhouse crop production. They've figured out how to maximize space and resource use efficiencies with greenhouse agriculture. What you see on the right is an interior view of a tomato production greenhouse in the Netherlands. And the concept of greenhouse agriculture is explicitly mentioned by Sir David in the film as not only a burgeoning agricultural sector, more profitable than field agriculture in many locations and in many scenarios, but also a key to a sustainable future, because they are able to produce more crops using much fewer resources. And if we're going to try to supply as many calories as are needed for 11.2 billion humans in 2100, we need to figure out a way to produce more food using less space. And so that's where greenhouse agriculture comes into the equation. There is an issue though, and it's the fact that greenhouse crop production systems are extremely energy intensive. Like I said, the whole point of controlled environment agriculture is, it's in the name, it's to control the environment inside of the structure in order to obtain optimal conditions for plant growth. And there are a lot of benefits to these types of growing systems. However, in order to control this environment, just like we control the environments inside of our own homes, you have to run a lot of different climate control systems, heating systems, cooling systems, ventilation systems. You need to keep air circulating in the space. You need to trigger irrigation pumps in many locations, such as the Netherlands. You can see that a lot of those greenhouse facilities, it's nighttime and they're lit up because they need to add in supplemental lighting in order to give the crops enough light to photosynthesize and achieve optimal growth conditions. So in fact, the top cost behind labor for greenhouse growers is energy. And a study that I like to point to often is this one. It was done in 2015, looking at lettuce production in Arizona. and Yuma, Arizona specifically. So Yuma is one of the top lettuce producers, lettuce exporters in the United States and in the world. This study done in 2015 was looking at what it takes to grow lettuce in a greenhouse hydroponic system. Hydroponic just means soil-less culture. You're not using soil to grow the plants. You're using oftentimes a liquid nutrient solution to fertilize and irrigate the plants. So what it takes to grow lettuce in a field hydroponic system versus in a more conventional setting in a greenhouse hydroponic system versus a more conventional field agriculture system. And what they determined was, you can see on the left, looking at the yield per square meter used in each of these systems. The hydroponic or greenhouse system shown in blue was 90% more efficient than the field production system in terms of the kilograms of lettuce produced per square meter annually. If you look in the middle at the chart in the middle, you can see the water use by the greenhouse system was less than 10% of what was used in the field. 10% in terms of liters used per kilogram annually. However, looking on the right, this is a log scale, so orders of magnitude, and it's looking at how much energy was required to produce a kilogram of lettuce in the greenhouse versus the field. And the greenhouse was orders of magnitude higher than the field setting. And because of running all of those electrical components and systems that we just discussed. So, this is a dilemma, right? We understand, based off of what David Attenborough has told us, our hero, as well as many other sources, that greenhouses are incredibly space use efficient, much more water use efficient and resource use efficient in general, as far as like fertilizers and pesticides and all of those inputs needed for an agricultural system. But the energy demand is huge. So we need to figure agrivoltaics comes into the equation. Agrivoltaics simply means the integration of agricultural systems like a greenhouse with photovoltaic energy, renewable energy. And there are many different system designs that can be used for agrivoltaics. And some of them are shown here. And the pictures you're actually seeing here is a summary of the agrivoltaic research that my research center in Tucson, the Controlled Environment Agriculture Center, has been involved with over the past less than a decade or so. So you can see in the top left image, ground-mounted, standalone, conventional solar panel or photovoltaic array, located adjacent to a greenhouse on the Controlled Environment Agriculture site. And that is an option, and this particular system design is used in many places around the world already. But again, going back to what we were talking about with the need to transition to renewable energies and land use balances, land use efficiency, in many cases, space is a very limiting factor. So what about if we could integrate photovoltaic solar panels onto the greenhouse structure itself? And so that's the theme dominating the bottom images in this slide. And on the left, you can see a unique type of photovoltaic material called a luminescent solar collector that's basically attenuating or modifying incident sunlight harvesting the other wavelengths of sunlight for electricity by the integrated photovoltaic system. And then on the bottom right of this slide, you can see I'm there in the organic photovoltaic integrated greenhouse. That was a part of my research experiments. And there, and I'll be talking about this obviously in more detail today, we're looking at another type of photovoltaic material, a semi-transparent, thin film, flexible solar panel that that has a lot of design and economic and environmental advantages, and we'll get into those details. So before we can talk about the systems integration aspects of organic photovoltaics with greenhouses, fundamentally, what is an organic photovoltaic? And I'll use the acronym OPV to save some time. But an organic photovoltaic is distinguished from an inorganic photovoltaic, such as a silicon solar panel that you might see on Thad and Linda's roof, based on the material ingredients that go into making an organic photovoltaic or an OPV. Instead of a conventional semiconductor such as silicone, an organic photovoltaic is based on these semiconductive organic polymers that, when combined, create a photoactive layer in an organic photovoltaic cell that can produce electricity when light is incident on the material. And the big thing to know about OPVs is the fact that they are solution processable. And this means that they can be made into inks or dyes that can be literally printed or coated onto a variety of different materials, of different substrates. And so this gives you incredible design flexibility with organic photovoltaics. Like I said, they can be printed, and it's particularly exciting because of the advances in printing technologies that have occurred in recent decades, and particularly roll-to-roll printing technologies that are high through cells, instead of a very energy intensive process that comes along with inorganic, more conventional solar panels. As I said before, OPVs, because they can be printed, they can be made to be semi-transparent. You can see through them. The variety of different substrates that you can print OPVs onto means that they can be flexible or bendable. You can also make these OPVs into a variety of different colors, so they can be spectrally customized. And this particular design feature is interesting from a design perspective, because if you can spectrally customize, make the OPV into whatever color, whatever make it absorb whatever light if you want it to. The theory is that you could spectrally optimize an OPV for integration with whatever system you want. And in a greenhouse, knowing that plants need certain kinds of light to conduct photosynthesis and other developmental processes, knowing what light needs are present in the crop, you can then make the organic photovoltaic onto the greenhouse structure absorb all of those wavelengths that are not needed by the crop in order to generate electricity. And we'll get more into that a little bit later on. But some other design advantages are also the fact that they can be incredibly lightweight, which is important for transport, storage, installation, deployment, all of those things. And then because of the fact that they can be roll-to-roll printed, it means that they're much more affordable, much cheaper to manufacture than conventional solar panels. And also environmentally preferable. You're not harvesting any rare earth metals in order to make an OPV, such as silicon. Instead, you are using abundant earth materials, polymers like carbon and hydrogen, in order to make a device that can convert light into electricity. So all of these design features have many different industries interested in the integration of OPVs into their products, designs, buildings, etc. So what you see here is one example of the integration of OPVs into our built environment. This is a shade structure located in Germany, and you can see on the right there those cubic designs are organic photovoltaic cells. They can be made to be a variety of different shapes and colors, and integrated into interesting architectural and functional structures in our environment. People are interested in integrating organic photovoltaics onto vertical building facades, and that means that you are taking space in our built environment that is otherwise unused and converting it into a solar energy harvesting surface. So that's hugely advantageous in terms of space use. Another example here is an electric car that is outfitted with this removable OPV embedded cloth that you can just drape over the car when you're parked in a parking lot. And if there's no charging station for your electric car, you can use this and use it to give you a small charge up while you're away from home. But looking at greenhouses specifically, this is still very much in the research and development phase, and that's what my work is a part of. But people are interested in utilizing OPVs in the greenhouse environment. Here you can see that they are adhered to the greenhouse sidewalls, as well as deployed as a shade sail in the greenhouse. And that's particularly interesting for areas of the world in which shade is needed in greenhouses, such as Arizona. And in the hotter side, typically deployed in utilizing OPVs as deployable, retractable shading screens, climate screens is also very much of interest to the industry. Right. So looking at research efforts that have been done for OPV integrated greenhouses in the past couple of years, I won't get into so much of the details with this study, but what's important to know is that it looked at the viability of an OPV integrated greenhouse in a variety of different locations around the United States, including Arizona, North Carolina, and Wisconsin. And this study was particularly interesting for me because it determined that a greenhouse, a standalone commercial scale greenhouse located in Arizona, outfitted with an organic photovoltaic roof, would be able to be net zero, or produce its own energy demand considering a lot of design assumptions about the organic photovoltaic material, how efficient it is, how much energy it can produce, what its spectral characteristics are. In addition to the operation of the greenhouse, what kind of crop is being produced, how big is it, how often do you have to run the ventilation, cooling, heating systems, etc. But what they determined was that a greenhouse, OPV integrated greenhouse in Arizona, would be able to meet its own energy demands based off of the electricity produced with an OPV system located on the roof. In addition to benefiting from the microclimate effects introduced by the shading caused by the OPV. And so for those two reasons, they determined that this system design concept would make a lot of sense in a place like Arizona for a greenhouse crop production system. Considering a place like North Carolina or Wisconsin, it's a little bit less clear if this would be as beneficial of a design because of the shading effects possibly interfering with crop light quantity needs, in addition to other heating and cooling system operation design considerations. So this is motivating for me as a greenhouse engineer in Arizona looking at this. This makes an OPV integrated greenhouse design concept not only exciting in concept, but also in application and feasibility. So when thinking about these OPV greenhouse tattoos, there are a lot of design questions that we should be asking. And that is, first, how much power can an OPV system produce? That's one of the biggest considerations with this technology. If you look at, again, a solar panel on Thad and Linda's house, that's 20% efficient. And by efficient, I'm just talking about how much power is the solar panel able to produce with a given amount of light. And I'll be talking about the OPV devices that I used in my own research. We were looking at efficiencies between 1 and 3% efficient for a commercially available large area manufactured OPV device. And that's a huge drop in efficiency. But the exciting thing about OPVs is the trends that's been occurring in the past decade in terms of efficiency. So as I just said, Thad and Linda's panels are probably around 20% efficient. For an OPV produced today, commercially, you're looking at more like 8 to 10% efficient. And then for OPV cells that are on the cutting edge, manufactured in the lab, now you're starting to see 18% efficiency. So that trend is increasing steadily and rapidly. And we expect to see more advances in even the next 5 years in terms of device efficiency, making this a much more viable energy generation source. Another consideration is how much does it cost? How much does an OPV device cost you? The panels that we used in our study were, well, I guess I should start out with, again, Thad and Linda's house. Those panels probably cost them about $2 to $3 per watt in the first 5 years. The OPV panels that I used in my study would cost you about $11 per watt in the first 5 years. So much more expensive now, but again, as the technology and the manufacturing processes mature in the next decade, we're expecting to see those costs decrease rapidly. Other considerations are, how should you install them? What's the best design configuration for an OPV on your greenhouse? Should they be installed on the outside of the greenhouse where they can harvest the most incident sunlight? However, they're experiencing a lot of mechanical stresses that are occurring, you know, wind and rain and all of these harsh climatic conditions that can greatly lessen the lifetime of the material? Or should they be installed inside of the greenhouse where they're possibly not able to harvest as much incident light because it's passing through that greenhouse cover before it can get to the OPV device, but they're able to last a lot longer? That's another big question. Related to the usable lifetime of the device, and is it going to last you 2 weeks, 5 years, or 10 years? That makes a big difference in terms of people's investment calculations for this type of system design. And after the usable lifetime of the material, how do I dispose of it? Is it recyclable? Is it recoverable in any way? Those solar panels on Thad and Linda's house, it's actually very difficult to recycle them, and people are trying to come up with new and better ways to recycle and recover conventional rigid silicon solar panels. But with OPVs that are printed on plastics, they're actually much more recyclable and therefore environmentally advantageous in that respect. And then finally, looking at the crops, the whole point of having a greenhouse is to produce plants and biomass. So what is the effect of the OPV on the greenhouse crop? As I said before, when you're integrating a semi-transparent material onto a greenhouse, it's going to change the lighting conditions that are present in the interior of the greenhouse. Is this neutral for the greenhouse crop? Is it beneficial because of the shading effect that's introduced, that's needed in many greenhouses around the world? Or is it detrimental? Are the OPVs actually harvesting the lighting, the sunlight wavelengths that are needed by the crop in order to photosynthesize? All of these design questions need to be asked when thinking about the integration of semi-transparent photovoltaic and specifically organic photovoltaic tattoos onto a greenhouse structure. So this brings us to my current research project. And this is looking at a high tunnel greenhouse located at my research center, in which we deployed these commercially available large area OPV arrays, or I'll call them rolls because they can be rolled, and that's how they were shipped to us. But deploying these onto a greenhouse structure and trying to assess them, assess them on how much electrical energy was able to be produced by these devices while deployed in a real greenhouse setting, as well as assess the greenhouse microclimate and crop response as a result of the shading effect introduced by these OPV rolls deployed on the greenhouse roof. And so the outcomes from this project was first, it was novel in that we were taking actually commercially available OPV devices, some of the first commercially available OPV devices, and characterizing the electrical performance of them deployed on an actual greenhouse structure. And there, as I showed you, there's a lot of research interest and a lot of industry interest in OPV applications to greenhouses, but a lot of it has just been speculation up to this point. So that's the true value here is we're taking a commercially available product and saying this is how it performed and here's how it can actually be improved if you want to make this system design actually feasible from an engineering perspective and a crop production perspective. And then in order to characterize the electrical performance of these OPV devices, remember they're curved as they're deployed on a greenhouse roof, on the one that we used at least. And so in order to say, you know, the OPV device is this efficient given this much sunlight incident on the device, we needed to be able to say how much sunlight at 10 a.m. on February 6th of 2020 was incident on the whole curved surface of the OPV device when we measured it, when we took an electrical measurement. So we needed to develop some novel methods in order to electrically characterize these curved PV devices. I'll be focusing on phase one in the rest of the discussion, just because we've already published on that, and we're currently preparing another manuscript for phase two. But briefly, phase two was the crop response and greenhouse microclimate experiment that we did following the electrical monitoring project. And this was important, hugely important, because you need to evaluate the overall design compatibility of the greenhouse system with integrated OPV devices. So we're not only thinking about how much energy can these devices produce, but also, as we discussed before, what the effects are on the crop and microclimate and all of those things that we need to know in order to say this is a feasible design or it's not. So for our device, this is looking at the OPV, for our project, this is looking at the OPV devices that we used in a little bit more detail. Each of these devices is about a meter squared in area, and an OPV roll that you see on the bottom are these is comprised of 8 individual OPV panels wired together in parallel, and then is generating electricity from those electrical leads located at the left side of the roll. But each of these OPV panels is actually 4 OPV modules wired together in series. And so you can see on the image on the top, on the upper left, each of those rectangles is an OPV, is a module, and a module is equivalent to a solar panel, a conventional solar panel. You can also call that a PV module. And so each of these modules is connected together and then making one panel, and then a panel is then wired together with 7 other panels to make an OPV roll. And what you see on the upper right are the nominal electrical characteristics given to us by the manufacturer of this OPV roll. And as I said before, these are commercially available, some of the first commercially available OPV, large area OPV devices. And you're looking at a cell efficiency of 3.3%. So fairly low, but you know, as I said before, trends are improving. So won't get into too much detail here, but essentially what we were doing is standalone energy monitoring of these OPV devices by sampling the current voltage curve from the OPV rolls. And what the current voltage or IV curve of a PV cell tells us, it's basically telling us how any electrical device performs in a circuit. And for a PV device specifically, for a photovoltaic cell, it can tell us some interesting electrical parameters, such as short circuit current, open circuit voltage, and how much power can be produced from the PV cell. So we're interested in using this, this method of analysis for characterizing the electrical performance of our OPV devices. I was talking about PV cell efficiency, and it's important to know, again, how much power can be produced by a PV cell given its area, and also the amount of sunlight that is incident on the PV cell. So the power conversion efficiency, or PCE, is calculated by looking at the power produced by your OPV roll divided by the incident sunlight times the area of the cell. And what I'm saying here in this, it's a fairly simple equation. We measured the power coming off of an OPV roll. We know its area, we know its surface area. What we don't know is how much sunlight is incident on the curved surface of the OPV roll at our times of measurement of the OPV rolls. So we had to figure out a way to calculate sunlight incident on a curved surface. And that's just what I'm talking about here, a program that we developed using some solar modeling software, PV system modeling software, in order to determine incident solar irradiance on the curved OPV surface for electrical characterization purposes. This is showing some of the model simulations that we were able to do with these methods. And what you're looking at on the bottom right there is a simulation of our greenhouse roof with an integrated OPV roll installed. And so what we're able to do with these methods is for each OPV panel, we're able to determine by breaking it up into small little segments, basically along the length of the roof, we're able to determine how much sunlight was incident at each unique angle as it rests curved on the roof, again, for electrical characterization purposes. This looks like a lot of data, and it is, but basically these are some of the electrical parameters that we're interested in measuring for our OPV rolls that were deployed on the greenhouse. And what to take away from this, the most important thing is there was electrical variability in these commercially available OPV devices, huge electrical variability. It could be the difference between 17 watts produced versus 70 watts, so 80% more power produced just based off of which OPV roll you're using, that are supposedly manufactured and made from identical materials and manufactured in the same way. Comparing the performance of 6 OPV rolls that were deployed on our greenhouse, this is looking at their efficiencies. Remember the power conversion efficiency metric that we're looking at over the course of a day. And what you're looking at here is essentially, it's indicated in green, yellow, and red. Green meaning highest efficiency over the measurement period in terms of morning, midday, or afternoon. Red meaning lowest efficiency. And what you see is that all of the OPV rolls that we measured actually had lowest efficiencies in the afternoon. And that is pointing to what's been widely reported in the literature. A unique thing about OPV devices is that they degrade over the course of the day. The photoactive materials experience some kind of degradation effect. And so you're starting to produce less power given the same amount of sunlight, or a unit amount of sunlight over the course of the day. It was inconsistent whether or not they were more efficient in the morning versus midday, however. I'm highlighting OPV6 and OPV7 as 2 rolls that were OPV6 our highest performing roll, and OPV7 our lowest performing roll. And I just want to highlight what I was talking about earlier, which is this electrical performance variability between identical OPV devices. And you can see here, looking at 2 different days of measurement that we took on these OPV rolls. The highest performing roll produced 400, and just focus on this figure at the bottom here, 405 watt hours, a unit of energy over the course of the day. Whereas our lowest performing roll produced less than half that amount of energy. And so what's important here is the fact that design consistency and manufacturing consistency is an incredible challenge with OPV production, and it's a very delicate fabrication process. And in order to make this an actually commercially viable system design, that challenge in the commercial production of these devices really needs to be addressed. And what you're looking at here is also, those same electrical parameters that we were interested in looking at for these OPV rolls at different levels of sunlight, of irradiance. And it's the same story. They do experience some degradation over the course of the day. Efficiencies in many roles are actually decreasing, as I said before, over the course of the day, and they're not necessarily more efficient at higher light levels, which is in contrast to conventional solar panels, which generally tend to produce more electricity with higher amounts of sunlight. However, because of the unique properties of this particular type of solar cell and OPV, these devices are actually better able, more efficient in terms of electricity production at diffuse light levels, so at lower light levels. And that is important to consider for where these devices should be integrated. Instead of being located directly on top of a roof with a ton of direct sunlight, integrating them onto vertical surfaces with more diffuse sunlight might make a little bit more sense. So some key takeaways from this project were, first, that this design concept is gaining a lot of traction. It's gaining a lot of attention in both research and industry. But up until this point, it's a lot of speculation. It's a lot of these OPV material science nerds in the lab are, creating these incredibly efficient OPV cells that are literally 1 inch squared, and then extrapolating that tiny cell performance to say, if we cover an entire greenhouse facility with these OPV devices, you could produce more than enough energy for the entire city or something like that. But the reality is we need to be testing devices that are commercially available and actually able to be deployed onto structures, such as greenhouses or whatever structure you'd like to integrate it into. So what our study did, what phase 1 did, is providing methods for evaluating the electrical performance and deployment configurations of commercially available large area greenhouse integrated OPVs. We observed large variability in the electrical performance of identical devices. And again, that's getting at the need for consistent and reliable manufacturing processes of these exciting devices. If you actually want to convince the industry, convince anyone with a greenhouse that, yeah, you should tattoo your greenhouse with these photovoltaic tattoos. It's a good idea. Future work will be evaluating, you know, as I was talking about before, different design configurations with OPVs. Do you want to put them on the outside, on the inside, on the sidewalls, inside the sidewalls? How much area do we need to cover with OPV devices in order to meet the energy demands of the greenhouse, and maybe have a little bit of supplemental electricity that can be diverted into the grid afterward. All of that depends on the greenhouse energy needs. You know, a high tunnel greenhouse with plants just growing in the soil and really no need for a heating system uses a lot less energy than a massively than a massive commercial scale tomato production system with you know, precision climate control technologies and all of that. So in addition to, you know, it makes a big difference if the OPV device is 2% efficient or 18% efficient. All of these factors need to be considered when determining the design feasibility of this. And that's what we're looking at with phase 2 of our project. Again, is overall resource use efficiency of an OPV integrated greenhouse and system compatibility, talking about, again, crop response, effect on greenhouse microclimate, energy generation potentials, all of that. And then again, the constraints on commercially available OPV devices that are imposed by the roll-to-roll fabrication processes need to be considered and addressed. And then we're also thinking about, for the engineering feasibility of this design, thinking about payback periods. You know, how long does it take you to get a return on your investment, in addition to energy payback period or carbon emissions payback period for a PV technology. So we're interested in addressing all of those challenges in order to determine if this is a feasible design, and if not, how to make it more feasible in the coming decade. So if you guys take anything away from this presentation, I know it was a lot of data, especially at the end there, but it's just the fact that photovoltaic integrated greenhouses mean food production and renewable energy generation year-round. And increasingly, it's obvious that those are two things that we'll need going into the future. So thank you very much for listening today. And these are just a few of the people and organizations that I need to acknowledge and thank for contributions to my research so far. And with that, I'll take any questions that you guys might have. Thanks again. Thad, I think you're muted. Thad, I think you're muted. Here, I'll send a chat.
There's quite a few questions on the chat.
Maybe I'll just take over, go rogue. One sec. All right. Okay. So I'm going to go ahead and read the question myself, I suppose, and answer it. So this is from Danielle Nagengast. Apologies if I mispronounced that. And the question is, does it make sense to only use them on the south-facing side of an existing structure? Does it make to retrofit a rigid-skinned greenhouse like the Sunrise greenhouse? Right. So I live just down the street from the Sunrise Community Farm Center, and I've noticed all of the greenhouses there, and it's super exciting. What is important to note here, and that's a good question about the south-facing side. It's not a terrible idea to integrate them onto the entire structure, because of what I said before about the device's ability to utilize more diffuse light in order to produce electricity. So there is going to be more diffuse light on the northern side of a greenhouse because of all of the reflection and non-direct light coming from the southward facing direction. So I would say for these particular solar panels, if it was a different type of PV technology like conventional silicon, I would say, yeah, it's probably in your best interest cost-wise, energy generation-wise, just locate them on the southern-facing side. But because you have the potential to utilize more diffuse light, locating them on the entire structure would actually would make more design sense. And then so she was asking about a rigid skinned greenhouse. So I would actually question, oh, right, there are two different kinds of greenhouses, I think, at the Sunrise Community Farm. There are polyethylene, I think there's polyethylene roofs, curved high tunnels, as well as polycarbonate, rigid roofs and A-frame structure. And you could definitely cover both types of roofs. Again, the advantages of OPVs is that they're flexible. They can go on a curved surface. They can also go on a rigid surface, a flat surface. It just depends on what you're working with. Okay, so from Joe Randolph, the question was, did the time of year and the longitude of your greenhouse location figure in the sun calculations? Yes. That have come out in the past decade, even with solar modeling and PV system modeling technology. The equations that I used are based off of work that was done in the 90s, 80s and 90s in terms of modeling the solar irradiance incident on the curved greenhouse roof surface. But the software that's available automatically considers all solar angle, solar position, time of year, time of day into determining the location and amount of sunlight incident on a surface. Okay, I'm gonna just skip ahead, make sure I answer some from different folks. So Lynn asks, we have used high tunnels for vegetable and flower production on our farm. The problem in Kansas is heat buildup, even in cold weather. Could a few of these rolls be used just to run a ventilation fan? Absolutely. And doing some calculations, as I told you guys, these devices are not that efficient compared to more conventional, commercially available PV technologies. But they are efficient enough to run a ventilation fan. So for my greenhouse, for example, we have these, high-powered exhaust fans. We run a pad and fan cooling system in Arizona. It uses evaporative cooling. but we also run horizontal airflow fans, which I think would be a little bit more appropriately sized for high tunnels, you know, for vegetable and flower production, in terms of the electrical consumption of that size of fan. And so an OPV roll, as I said before, our highest performing roll was able to produce around 400 watts, 400 watt hours over the course of the day. So you'll just have to do the calculations here, given your you know, solar installation in Kansas, how much power could be produced from an OPV roll. But I would definitely say that running a ventilation fan for a small scale greenhouse is totally in the wheelhouse of these types of OPV devices that even I was looking at in my project. Okay, and then Daniel or Danielle seems particularly excited about this. 3 questions, but another one from Daniel is, so the OPV can harvest the diffuse light from the interior of the house also, correct? E.g., both sides of the array can collect, unlike a rigid photovoltaic. Yeah, exactly right. So not only are they more capable of harvesting diffuse light, but they're also bifacial. And so light that passes through the top layer or layer that is exposed to instant sunlight then transmits to the ground, reflects back up, and can actually be harvested on the underside of the OPV device, making it more efficient because it can harvest light for energy production from both sides of the device. So that's an interesting point. It's a good point too. Remember, greenhouses aren't the only system that people are interested in applying the OPV technology to. They're interested in using them indoors, even like sunlight, where sunlight isn't even present. It's just artificial light from lighting systems inside. People are interested in integrating these types of solar cells into the interior buildings for light harvesting, making it you know, a more efficient use of space and also electrical light energy. So that's a good point as well. Cool. So I think I'll try to get one more question. Yeah, okay, from Daniel again. I like all these questions. If you deployed them as an interior sail on a rigid greenhouse, can they easily be rolled up and redeployed to respond to sunlight versus cloudy days? Can they also provide much R factor insulation when deployed? And it's almost like I paid Daniel to start asking me these questions, because this is everything that I'm interested in my research looking ahead. But I personally think that the modular deployment of OPV devices in a greenhouse will be the direction that this is headed. And that is looking at, in an image we saw, that shade sail deployed in a greenhouse. And that's deployable and then retractable. And because these are flexible PV cells, they can be, you know, rolled up with, like a curtain in a greenhouse. And if you operate these, as many commercial greenhouses do, in an interior sail, like as they do for climate screens or shade screens, they, you know, deploy them in the hotter months when you're trying to create more shade in the greenhouse, and then retract them on cloudy days when you're trying not to interfere with light needed by the crop. So theoretically, OPV devices could be OPV embedded interior shade screens could be operated in the same way. And depending on the other materials that are used to create this shade screen, to create this textile, you could have a huge insulation effect from this device, depending on what your goals are and what your needs are with a greenhouse climate screen. I think we are about out of time. Unfortunately, Thad and Linda are still muted. I know. But I guess I'll just wrap up here. I don't see any other questions. Thanks again. Thanks again for listening today. I really appreciate all of you showing up. And I think you'll be hearing from Thad on next week's Earth Care Forum presentation. But yeah, I hope to see you, everyone who lives in Lawrence, around. And yeah, thanks again for listening. So
Thank you.
yeah, have a great Sunday, everybody.
Thank you. You too.
Very much.
Yeah.
There you go.
Thank you. Bye-bye.
Thank you, guys.
Thad, you're on mute.
That's been on mute all the time.
Yeah.
You can probably hear us though.
Yeah, I see he's talking. Yeah. Thanks, Thad. We'll see you next time.
Thanks for the presentation.
Okay, I'm hanging up.
Okay. I'm gonna go turn on the TV and bring
Yep.
up the church service.
Yep, you got it.